Hello everyone. Today I'll be discussing on the topic Hungarian algorithm. Let us first look who developed and published this algorithm. It was done by Harold Kuhn in the year 1955, but who gave the name to it as Hungarian method? Because the algorithm was largely based on earlier works of two Hungarian mathematicians named Denis Koning and Jenő Egervary. Now first let's look into what Hungarian algorithm is. It is an application which is used to find minimum cost of assignment problem using bipartite graph matching. What is an assignment problem? Assignment problem is used to assign source to the right destination such that the total processing time or cost is minimized. The most important thing to remember in Hungarian algorithm is that it deals with finding out the minimum cost of the problem, which is the optimal solution when we look into the assignment problem. This is done with the help of bipartite matching. Bipartite graph is one such graph in which the set of edges chosen are in such a way that no two edges share an endpoint. And the maximum matching is when there is this maximum size, that is maximum number of edges are involved. Now, to solve any problem using the Hungarian algorithm, there are a few steps that are required to be followed. And if done so properly, it is said that we definitely will find out the most optimal solution, that is the minimum cost of that graph. We will look into an example in future slides, but first let us understand what the steps of the algorithm are. Step 1 is that we have to make an adjacency matrix of the given graph. The graph given here is the bipartite graph. The bipartite graph, as read earlier, was one such graph where no two edges have the states start and end point. After forming this adjacency matrix, we perform row and column reduction. That is step 2.1, which is row reduction. What we do is that we find the smallest number in each row and subtract that number with all the entries of that particular row. And this gives rise to another table when followed for each row. From this new table, we perform step 2.2, which is column reduction, in which we find the smallest value of every column and perform subtraction with all the other entries of that column, and giving rise to another table. On this new table, we perform step 3, which is optimizing the matrix. This is done by finding the minimum number of lines covered, all zeros. And this is done by row scanning and column scanning. Now, what is row scanning? It is step 3.1 and it states that going from first row to the following consistent rows sequentially, we find that row which has exactly 1 0. And whenever we find that 0, we mark a square box around that 0 and draw a vertical line across that entire column passing through that 0. And if we do not find that row, we simply skip that row where we are considering that 0 and move on to the next row. Then, after performing row scanning, we see whether all the zeros in the matrix are covered with lines. And if that is not the case, we go to step 3.3. When we go to step 3.3, we perform column scanning, which follows the same procedure as row scanning, but here we find exactly 1 0 in all the columns sequentially and make a square box around that 0 and draw a horizontal line across that entire row passing through that 0. After doing this, we go to step 4 and check if the number of square boxes marked are equal to the number of rows in that matrix. If yes, then we go to step 8, and which means that we have optimized the matrix completely and we have to just find what the minimum cost is now. But if that is not the case, we go to step 5. Step 5 is when we have zeros remaining in that graph which are not striked off. And the other values also are present in the graph. So in step 5, we find that minimum value of all the cells that are not covered with lines. And these cells are also called undeleted cells. Step 5.1 shows that we take that least value of the undeleted cells and put it at the intersection point of the lines in the present matrix, which are formed after row scanning and column scanning. In step 5.2, we take that minimum value and subtract them from all the undeleted cells which are remaining. In step 5.3, we have to make sure that we do not make any changes to the value 0 and remain them the same. After this, we go to step 6, which is that we have to do all the procedure again from step 3 onwards, which first deals with optimization of the graph and then checking for the square boxes and the number of rows. After doing this, we see that if finally the square boxes are equal to the number of rows, and if still they are unequal, we perform diagonal scanning as stated in step 7.1. In this, we find all those zeros which are marked in boxes in that matrix and find any diagonal to that zeros. Now, this is a way of putting those zeros also into square boxes and similarly striking off the corresponding columns and rows by horizontally and vertically. And after doing this with one consequent diagonal, we take that new zero which is marked into the square box and see if there are any other diagonals with the zero present in it and do the same procedure with that also. After doing all of this, it is certain that we have reached the final solution where the number of square boxes is equal to the number of rows in that matrix. Now, this is how we know that which all edge will be taken or will be considered when we have to find the optimal solution. Now, it is most important to remember that it is not important that we find only one such solution or one such pattern or sequence of edges which gives us the minimum cost. We have to remember that there can be multiple optimal solutions, but the most important point is that the minimum cost will always remain the same in each solution. But now comes the point as to discussing how do we calculate the minimum cost. We calculate the minimum cost by replacing the values of the weights of that edge and by adding all those weights of all the edges that are discovered from the Hungarian algorithm. And when we add all those weights on these edges, we find the minimum cost of that bipartite graph. Let us look into a simple example of the Hungarian algorithm implementing the steps that were just discussed. In figure 1, it is shown a bipartite graph having edges which are different in all ways. That is, no two edges have the same start and end point, and all these edges have weights on them. We form an adjacency matrix first in step 1, and let us consider the nodes on the left side to be our rows and the nodes on the right side to be our columns. And the matrix is filled with the corresponding weights on these edges. For example, the edge from A to 1 is 160, and that is how it is mapped in the matrix in figure 2. Following the same procedure, for B1, C1, A2, B2, C2, A3, B3, C3 with respect to the graph. After making this matrix, we move on to step 2.1, which is performing row reduction. The first step is that find the minimum values. So when we refer to the graph, to the matrix made by the graph, we can see that in row A, the minimum value is value 140. Similarly, in row, like we have shown here, similarly in row B, the minimum value is 150 and row C it's 160. As referring to the figure 2, that is the matrix that we have made. Now, when we take the value of row A, that is 140, and subtract it from A1 value, A2 value, and A3 value, and doing the same with all the other minimum values with their corresponding rows, we form another new matrix, which is figure 3, in which after subtraction, we have a new set of values. Now, performing step 2.2, which is column reduction. Now, we take this new matrix and find the minimum values of column 1 has the minimum value 0, column 2 has the minimum value 0, and column 3 has the minimum value 50. Now, when we subtract these minimum values from all the entries in that particular column, we find figure 4, and the values are present after subtraction. Now, after this, we move on to step 3.1, which is row scanning. Now, row scanning is performed that first we will go to row A and find if there is exactly 1 0 present. We can see that yes, there is 1 0 present, that is at A2. When we take that into consideration, we mark a box around that particular 0 and strike off that entire column. Now we go to row B and see that no, there are 2 zeros present, which is not taking into consideration that row. Now when we go to row C, we see that yes, there was 1 0 present, but it has already been striked off because of row A, thus giving rise to figure 5. Now, taking into consideration step 3.2, we perform column scanning on figure 5. We go through each column and find exactly one number of 0. Now, when we first go to column 1 in figure 6, we can see that we have found exactly 1 0. So we mark it in a box and strike off that entire row. Now, when we see step 4, now we have to check if the number of squares in that matrix, which is figure 6 here, is equal to the number of rows in the matrix. So we see that there are 2 squares, but the number of rows are 3. Hence, we know that both of them are not equal. So we do not say that we have reached the optimal solution. To further move on, we go to step 5, which is finding minimum value of the undeleted values. Here, the minimum value of all the undeleted values is 20. Now, what we do is we add this at the intersection point of the lines and subtract 20 from the rest. Now, we have to perform these changes on figure 6. So, we have to add 20 on B2 and perform subtraction of 20 from A1, C1, A3 and C3. And we have to also remember to not make any changes to the 0 values, that is B1, A2, C2 and B3. So giving rise to figure number 7. Now on this new matrix, we have to perform row scanning. Now on doing that, we see that there is no row which has exactly 1 0. Hence, we know that with the help of row scanning, we will not reach to the optimal solution. Moving on, we form and perform column scanning on this matrix. So when we go to column 1, we see that there is not exactly 1 0. Column 2, not 1 0. But on column 3, we see that there is 1 0, which is B3. So we mark B3 in a box and strike that entire row, giving rise to figure 8. Now we check if the 0 in this column are equal to the number of rows in this column. So we can see that no, this is not the case. It is not that. Now we go to step 7, which is performing diagonal scanning. What we do in diagonal scanning is we see that B3 was the zero marked in a box in the figure 8. We see that there are two diagonals of that B3 box, which is A2 and C2. So taking both of them separately, first in diagonal A2, we see that there is a zero. So we mark it into a box and strike that entire column. And similarly in C2, we see it's a zero and we mark that in the box and strike the entire column. Now further seeing, the diagonal to A2 is C1. Why is it C1 and not B1? Because B1 has already been striked off. Or similarly, then we take that C1 value and put that in a box and strike it with a vertical line. And finding the diagonal to C2 is A1, and we put that in a box and strike it with a line. So now we can see that since on comparison, there are total 3 number of boxes in both the solutions and there are 3 number of rows in the matrix, we see that both these solutions will give us the most minimum cost, that is the optimal solution. Now, on finding the minimum cost, if referred earlier, we see that from A to 2, the edge had the weight 140. From B to 3, it had 200. From C to 1, it had 180. This is when we consider the first solution. We can see that these edges, A2, B3, and C1, are the ones that are marked in the boxes in figure 11. Now, when we do the summation of all these edges, we find the total cost to be 520. Similarly, for solution 2, we see that A1 has 160, B3 had 200, and C2 had 160. And when we do the summation of this, it turns out to be 520. So what we notice here is that even though there are two different solutions, but the minimum cost of the graph will remain the same, that is 520. So this is the implementation of Hungarian algorithm in a problem, and how we, on step-by-step solving of it, we find the minimal cost without any difficulty and without any errors. Now, when we look deep into it, we know that it is applied in assigning jobs, for example, and this is done by one-for-one matching to identify the lowest cost solution where each job must be assigned to only one machine. So why is it so important and beneficial is because it gives us the minimum cost, which is to be remembered always. And we always require minimum cost because it will result in lesser computation time and faster development of our process. So it is beneficial for that. But on further research, we also find that Hungarian algorithm can be used to implement traveling salesman problem also. Just giving a brief about the traveling salesman problem, that it states that given a list of cities, the distance between each pair of cities, what is the shortest possible route that visits each city exactly once and returns to origin city. So in this also, what we have to remember is here also it's asking for the shortest possible route, which means indirectly that they want us to find out the minimum cost being the optimal solution. So I think that it will be easily implemented by Hungarian algorithm because the main point of the algorithm is to find the minimum cost. And with this, I would like to conclude that Hungarian algorithm should be remembered as an application which is used to solve the assigning problem, which is finding the minimum cost to assign a job. And it is done with the help of bipartite graphs. Thank you.